And for the robot programming, some tasks typically performed using one of the following weekend programming online or offline. With online programming, that's the way we use the dependence or by listening through programming. And with the offline programming, it's by using the programming language of each companies. This means the kind of robots. And another one is the task level programming. So the first one with the online programming, we use the dependence. That is a handheld device with a switch that's used to the control the robot's motion, and it can be considered as an interface between the users and the robot. And in this dependent is been linked to the controllers or the CPUs of the controller of the robots. So the endpoints are recorded in the controller's memory. And sequentially play back to execute the robot's action. The territories that can be determined by the robot controllers. But the intermediate point inside the territories normally that will be taught by us. So this kind of control methods with the use of the dependence is suitable to the point-to-point control application. And with the dependence, maybe it can have us easy to use. We can control directly and no need some kind of special programming skill. So the use of the dependent can be useful for the case that maybe programming the robots for variance and for repetitive tasks. And with point-to-point control, the speed is high, so it can be for the high-speed control. So besides using the dependence, we also can use the list through the programming. So for this, we can lead the robot physically through the required sequences of motion. Yeah, of course, by using dependent, we can also teach some intermediates. Or inside its workspace, there's no obstacles. So we can give it to move freely from the start point to the end point. And by this, through the programming, maybe the trajectory and the end point will be recorded. And by teaching, we give them, or we give the robots, some sampling routines. With the record points at around 60 to 80 times per second. And after that, we let the robots play back the results. And if it is in smooth, continuous motion, and thus we can operate the robots automatically. With this kind of programming, it will require the large memory. Maybe for a traditional robot with the previous version, the memory is a problem. But so far, when the data can restore in some ways, if we connect the robots to a network, so it's not a big problem. But in order to make the programs, the robots more professional, of course, each firm or each company will develop their own programming language for their robots. Because actually the robots, in order to work effectively, it will be connected to some kind of external sensor. Thus, a way can have or to provide the real-time trends beyond the sensory equipment. And another problem is when confused by beyond the geometry of the environment. And as you know now, the robots, of course, is not work for itself. It's also incorporates with other devices and machines in the automatic or automation system. So in order to make the robots can accomplish with the CAD/CAM system, so it needs the program. But the problem is, so far we haven't got a common language for all kind of robots. And each company have their own language for their robots only. And Maybe the programming language also can help us to programming offline while the robots are working for a different task. And we can see that so far we have a large number of robot languages available. At least here we can see that the AML, VAR, R, Braille, or Robot Studio, and etc. And it's around 200 language. So, if there is no standard exists, it's a problem. Because, for example, when we study at our university, we can have study some kind of robots that we have here. From the Honda, from Kuka, and ABB. And after that, maybe when we go to work in the future, other news companies will use another kind of robot. And we have study again how to be familiar with that kind of programming language. So if there is no mechanism or the standards, it's a problem because what we have learned will make no sense. And I think that's maybe in the near future when robots is more and more popular in our daily life, service, and in industries. Maybe a communities of the robots manufacturers, they must work together and find a solution. The same as the CNC machine in the previous part. We must have a standards or standardization for the CNC programming language. And now, so for the robots. So how do we measure the performance of robots? Maybe through the speed and accelerations, resolutions, the working volume, accuracy, cost. And you can see this. If we mix or we plus all these kind of evaluation function, it means that we talk about the AI system. That's what we develop now in the field of robots. And in the various of the 4 industries. With the speed and accelerations, of course, the faster speeds often reduce the resolution or increase the cost. And it varies depending on the person or the load. And the speed also will be limited according to the task of the robot perform. For example, maybe it's only the moving without loss, of course different with loss. And the welding, of course, different with the cutting task. For the resolutions, you see, can be often a speed trade-off, and it can be considered as the smallest movement of the robots can make. And increase resolution, it means to get a more accuracy portions of the movement. Of course, the speed will be reduced. Okay, sorry, let's continue. And with working volumes, this means the space within which the robots can operate. So with a larger volume, maybe the cost can be increased with the capabilities of the robots. So you see that in order to get an optimum values of all criteria for the performance of a robot, this means we have to solve a problem with some variable, and we have to determine which criteria for the specific task is the most important. And that's the way we can solve the problem and make everything that can be fine for the task. So tomorrow problem of the robots in the future. About the mechanisms, we must answer the question, what should the robot look like? And the actuator sensors that can be used for the robots. What kind of the actuators and sensors? And related to the estimation and learnings, it can be the reinforcement learning, graphical models, or learning by demonstrations. And for manipulation, the problem will be raised as what's the fast size of an object look like, and how heavy it is, and how hard should be gripped, or it can be rotated or not. And some kind of specific application, for example, with the medical robotics, such as develops, and maybe will be developed more in the future with autonomous surgeries. And the elder care is also a potential direction for the medical field. And biological robots with the biomimetic robots or the neuromatics. And navigation problem, how to avoid collisions, and some solution for the slam and explorations. And now in the intelligent environment, actually, the people now have developed some kind of self-acting robots with self-fixing, for example, little release and the electric release. It can recharge the batteries or energies by itself. Cell replicating, repairing, assembly organization, and reconfigurations. And we already have some movies that demonstrate for this kind of robots. And in fact, the scientists also developed some in some laboratories, and some are already to become a commercial versions. And actually now, you can search on the YouTube. Some scientists also develop some kind of new projects for developing the controllers of the robots and the robot's interface with the intelligent environment. For the human-robot interactions, because we have to answer the question why we need the robots. Because it was created to help us or to replace us. For example, with the social robots in the care context or home context or in industrial context. So we need to develop the comprehensions with the natural language, ground knowledge of questions, and you can see that with the service robots. The robots now are getting smaller and cheaper. And last time we already mentioned about the vacuum cleaner robots. It's now very cheap. Maybe we only pay a half month salary to buy one. And now the humans need to interact with and instruct the robots. So we need the robot can be understands or understood what we say or what we act, our action. So what we need to develop about the language, gesture, demonstration. And the language can be learned from the data and follow the instruction in the previously unseen world. So how the robots can study? And we already have some kind of definitions about the machine learning, deep learning, and they are still in investigations so far. And another task that we also need the robots to help us related to the safety or the security. So for this kind of fields, maybe some kind of ubiquitous robotics or the smaller and special purple robots. Or that we call spy. And how the people or the human can handle it to make the robots can understand what we say and understand what we do and understand what we would like the robot to do. So it's a problem to the scientists. And for you guys, yes, if you want to work more in the field of the autonomous robots or the humanoid robots, not only in industries with the industrial robots, maybe industrial robots is only invented and created for some kind of specific task. But for the service robots in the intelligence environment, it's still a problem for us now and in the near future. But I believe that with the AI and the big data, IoT, maybe in near future, we will create a new era for the robot manufacturing. So that's why for the mechatronics field, robotics and the intelligence mechatronics is a hot field for students to apply for. And do you know the number of applications that submit for the field of robots and intelligence system? Now it's rather than the number of students in the field of the traditional mechanical field. And for the human-robot interaction in intelligent environments, for personal service robots, controlled and used by untrained users. So it must be intuitive and easy to use interface. And of course, must be eliminate the dangerous instruction and fight close person actions. And in order to make the robots only intermittent commands, receive the intermittent commands, maybe the robots will be require an autonomous capabilities, and the use of commands can be at various levels of complexities. And you now can see that, for example, we have the Googles, and it can be considered as an AI system. You now can talk to the Google and it can answer you. Have you tried or not yet? And in order to make the humans can live, I must say live, with the robots in near future, of course, the human have to feel comfortable around robots. And of course, at that time, the robots have to communicate intention in natural way. So, maybe there's many things that we need to develop and investigate. That can be include the graphical programming interface or the GATX interface or the voice recognition. But there are some problems. For example, with the first one, it requires the sustained understanding of the robot. And the second one, how the robots can interpret the human gestures. The third one is the biggest problem is the robot's action corresponding to the words must be defined before. So, for the robot's communication device, we may have some easy to understand with the computer screen. and the speech synthesis and robot gestures. And for example, with Sophia, we already have some results with her face according to the announcements of the manufacturer. And an extra problem is, in the future, we must answer the question and some problem we have to interface with. How the robots can adapt with the human environment, and how can we can adapt with the environment of using many robots. So maybe in the future, robots can learn, can interact smoothly with people, and robots has artificial intelligence, and robots can mix other robots. So in conclusions, the robots are important components in the intelligent environment, not only in industries, but also in our daily life. They are automated devices and provide us with physical service. And they are autonomous control system, and it have simple and natural human robot interface. And it can be adaptive and learning capabilities. And robots have to maintain safety during its or their operations. So far, only very simple robots for simple tasks in intelligent environment exist. But in the future, with the development of the IT, information technologies, the robots sooner be developed more, and they become more and more intelligent. So, a big question for us is, when the robots will take over the world? And at least a question or problem we need to answer. For example, here is a decision which the machine makes without human supervision. Or may machine intelligence system make mistakes. And may intelligence system gambles when uncertain. Or another question is, can intelligence system exhibit personalities? And how much information should machine display to the human operators? And what we talk for fun is, we create the robot to help us, And if they have their own intelligence, so how the problem we can deal with that to make the environment in balance, or in some kind of movie they already mentioned the both robots at that time they will raise a new question: why the robots need to help or to serve the people or the humans? And that is a big question for us in the future, because so far we haven't got uh, any idea about if it happens or not. So step by step, maybe we will find the suitable solution for some kind of risk. And that's the and for the introduction about the intelligent environment with robots. And we come back to the industrial robots with the traditional robots. And in the next chapter, we will solve the problem with the kinematics problem for the industrial robots. And for this part, we must take a review of some mathematical problem with the calculus. So we move to the part of the transformation. We start with the 2D transformation. And you see that the robots that's created by the link and the joints connecting together. And solving the problem with the kinematics. Here, the first one is the forward kinematics. We know the configurations. We need to find the end effector of the robot. And in order to solve that problem, we need to use the transformation. And we take an overview for the transformation. That's what you have learned in the past with the calculus. So the questions we must answer is the why need the transformation, and how many kind of basic transformations, and how to combine the transformations. The first one with the transformation, you see, for example, we have train, and the trains have its wheel, and it has its own coordinates. But the train is moved in the world. each person related to the world, and we need to determine the relation. And by that, we create a frame to make the relation or to find out the relation, to determine their status. And in the environment, of course, it's work and it also has work with other. It means the interactions. And many certain situations, and maybe the near future we need to solve is about the control, how it can work together. This means how we determine on the status of the object in the environment. So it's can be monitoring, instantiations, viewings, and we need to animate. So the first question we must answer is why transformation? We have the model of the objects. The world coordinates can be determined by the distance, kilometers, millimeters, etc. And we can see the example for humans. It includes the torso, arm has leg, two legs, and the arms is contributed by the upper arm, lower arm, and hand, and etc. So we have some kind of transformations to models and to views through the zoom in or move drawings and make the animation. And for the transformation, we have the first one is the translation. It's the translate over vectors. We have the tx and ty's. And for this, we have a coordinate system that we call Decatur's coordinate system. And the positions after a movement can be determined as the x when we have an increment according to the x-axis and y-axis are tx and ty respectively. Thus, the new portion in the relation with the old ones will be set up via a matrix calculations according to these expressions, in which the new and the old are two vectors. It's a column matrix. And in this way, this situation, the T is also have the same form. And similarities for the polygons. The translation of polygons, we apply the same operation for all points. So works always for all transformation of the object, we define a set of points. The second kind of transformation is rotation. With the rotation, for example here, we still have the coordinate system, and we have the original point P here, and we make it rotate around the O. It means the origin of the coordinate system with an angle of alpha. And we have the new positions will be acquired equal to x cosine of alpha and minus with the y sine of alpha. And it's the same for the x sine alpha and plus with the y the sine of alpha. And its relations, we set up a form of the matrix multiplication between the coordinates of the original ones and a rotational matrix. Here are the R's. And to find this, we already do in the previous part. It's easy, right? Yeah, we have this here. And we find the new relation to the old one. And through, for example, is theta. And here is the rotation around this original point. This means the O. And what is the problem? If the original point is not here, what happens if it's move around here with the M and maybe it's this with the alpha and how we determine the P2 persons. And do you still remember the methodologies for the calculation? If anyone still remembers how we determine the P2, the scale of the M, yeah, is different from the 0 point. How we deal with that? Here the M is the origin is not simultaneous with the O as the 0 point of the coordinate system. Yeah, for example, we have this case. The news origin is Q, and a rotation over an angle of alpha, a P, to the new process. No. And of course, we have this. And the rotation increase Q over an angle of alpha. We determine the new process according to this is the new expression with the Qx and Qy. Its coordinate address of the Q. And each at that time the Q's also take the movements. For example, here we have the P's take the rotation around the originals of the coordinate system. And this one is also take the movement. And as that case, how we determine the process of each point. Maybe the transformations will be masses. And the transformation with respect to points even more masses. The problem is how to combine the transformations. We have translations and we have rotation. The form of the matrix is different. And if they maybe can make a series of transformation, and how we combine these, that's a problem. So for this case, how we can deal with that? Two different kind of form of the transformation must be unique in a common form, and we need to find out the common form. So that's why we give a new definition of the homogeneous coordination. Yeah, for homogeneous coordination, we can uniform the representations of translations, rotation, or scaling. The anomalies apply for the field of the robot transformations or robot calculation. We often use the translation and rotation. And we uniform the representation of points and vectors and compact representation of sequence of transformations together. So in order to do this, we add an extra coordinate with the S is the razor varies. So in the new homogeneous coordinate system, we have the vector p's will be expressed as the px, py, and ps, or the x, y, and s. And the relation between the Cartesian coordinates and the homogeneous coordinates is set up by the relations of the x. The xs will equal to the x divided by h. And in the case of the s equal to 1, in that case, we will set up the new. For example, here we have the xs and equal to the x by h and y equal to the y divided h and h equal to 1. In this case, we will have the h equal to x and ys equal to y. So the two systems are the same. So the expressions of the p xy will be equal to the p x y and 1. So we call this is a homogeneous coordinate system. And now we find out the form of the transformation. The form of the transformation in this situation will be set up with the new percent of P equal to the M and multiple with the T. The M is a transformation matrix. And we have this one. It has the form of the S one, and this one has the form of the X, Y, and 1. So you can see the size of this matrix is 3 rows and 1 column. 3 rows and 1 column. And this one must be a 3 by 3. 3 row and 3 column, right? Okay, so both the transformation matrix of the translation and the rotation are set up in this form. So we find out the rotational matrix or rotating matrix and the translation matrix. First one is the translation matrix. We find out this result. And where is it from? And we have this, the original. It's a set of equation in which we have is x and plus with the tx and new y and plus with the gy. So how we change from this to this? Yeah, in homogeneous system we have the 1 equal to 1, and from this we train thus with and 1 that's equal to, we have the form of the matrix multiplication. So here is x, y, and 1. So x, y, and 1. Here is x, y, and 1. Yeah, I use cursor, so it's a little bit ugly. Yeah. Guys, can you still recognize the characters? So after that, we fill in with the coordinates. Here is 1 and plus with, here's no y, so here's 0 and here's One is no, I was wrong. It's y, and plus with the tx, and do similar for other equations. We have 0 and 1 and gy, and here's 0 plus with 0 and 1. So we set up the form of the matrix as shown here. 1 0 0 1 0 0 and 0 1 0 and tx gy 1, tx gy 1. Yeah, and it has the form, and we define by the tx and ty. So this is a transformation matrix for the translation, and the same for the rotation. Yeah, same for rotation, because we have the new coordinates that equal to the cosine of theta and multiply with x and minus with the sine theta multiply with y, and we have set this form. And how for the inverse transformation? The inverse transformation is set by the -1. We have the form of the transformation of minus tx and ty. And about rotational is the minus of theta. And now combining the transformation. For example, we have the first transformation as the m1 multiple with the piece, and the second transformation matrix is the m2, and we have the second piece, and combine by multiplication of the matrix together, but it has its order. The order of the matrix must be fixed because the matrix multiplication we cannot change the positions of the matrix. Change the positions of the matrix maybe lead to the result is different. And now we take the specific case with the translations. The first translation and the second translation, and after that we combine T2. We have the T2 and the T1, and it is the consumption of T1 and the T2. It's the sum of the two coordinates portions of the values. And we define as the T of the T1x and plus with the T2x and T1y. Here is T1y, sorry, with the T2y. And then we do the similars with the rotational transformation. We will have the r theta 2 and r theta 1 will equal to the r theta 1 plus theta 2. And now if we have the rotation around one point, for example, here we rotate over the angle of theta around the point R. And R here is not concise with the originals of the coordinate system. So in this way, we must do 3 steps. The first one, we move the temporary originals, translate to the originals of the coordinate system. Which means that we have this is a new coordinate system, and we move to make the two coordinate systems are concise. And after that, we rotate over an angle of theta around the origins. And here we have the form of the matrix. And after that, we translate back to the temporary original points. And we have get the results of the rotation around P R. So in the form of the calculations, we will have The first step with the form of the translation with the increments is a minus of r's and ry's. The second is the same for enormous rotation around an origin with a theta angle. And the third one is the translations of the i's and y's, and we get the results. So, at last, we will set up the form of the expressions is a t multiplied with r and multiples with the t and the originals. So we see that which step we implement first when we stand near the objects, near the original objects, and after that the second and the third. The nearest one is the first, and we can see that's the sequence like this. Here is the target, and here's the original point, and here is the procedures. So the order this must be fixed. Okay, so for today we will stop here and we will continue in the next week.
Okay, sir.
Any question?
No question.
Okay. So see you guys and have a nice weekend.
Yes, thank you, sir. See you next week.
Okay, see you next week.